Hello everyone. Okay, so in this session, I'm going to deliver a lecture on the virtual work method for Truss. In the previous lecture, I have discussed on the Truss analysis, how to determine the internal forces in the truss by using the method of joint and the method of section. Okay, so in these sections, we will learn how we can use the virtual work method to calculate the displacement in the truss. Okay, so without further ado, let's discuss in detail. Okay, so in this slide shows the equation of a virtual work method for truss. So basically, we have seen these equations in the previous topic, which is on the beam topic. So I have shown to you these particular equations. So in fact, we have seen the equation of a virtual work method for the beam. So in this session, we will discuss in detail how we can use this particular virtual work methods in order to calculate the displacement in the truss. Okay, so the equation, what you can see in this slide is equal to the summation of N L over AE. So where you can see that they have a two N, which is small n, and capital N. So the small n is referred to the axial force that you can get it from the virtual work diagram. Okay, so meanwhile, the capital N is the axial forces that you can obtain from the real diagram. So we will look into in details in the example. Okay, so L is the length of a member in the truss. AE is the A is referred to the area, E is the modulus of rigidity. So the AE term is referred to the axial rigidity of truss structure. Okay, so you can see that in this equation, so you need to sum up all the entire member that form the structure's truss, okay, in order to calculate this displacement at certain joint in the truss system. Okay, so besides the load effect that can induce the displacement in the truss structure, so they have another effect that can cause the displacement in the truss. So while you can see here the temperature change in truss. So the temperature change in truss also can induce the displacement in the truss structure. So where you can use this particular equation to calculate the displacement of truss due to the temperature effect. So the equation is given by the summation of N alpha delta TL. Okay, so the N is referred to the axial forces in the virtual system diagram. Alpha is the coefficient of thermal expansion for member. So and delta T is the temperature change in member, while the L is as usual, this is a length of a member. So and again, you need to take into account of an entire total length that affected by the temperature change. Okay, so the total member that affected by temperature change. Okay, so besides the temperature change, there is another effect that can cause the displacement in the truss system, which is we call it as a fabrication errors in the truss. So the fabrication error in the truss can be calculated, means that the displacement of a truss due to the effect can be calculated by using this equation, where it is given by the summation of N delta L. So which is delta L is referred to differences in the length of member from its intended size as caused by the fabrication error. And n, the small n as usual. So this is referred to the axial force in the virtual diagram. Okay, so let's discuss in detail on all this effect in the example. Okay, so let's discuss on example 4. So what you can see in this example, we have a simple truss which is consists of 3 members in the structure system. So it is supported by the pin and a roller at the A and B respectively. So and in this example, so we need to calculate the displacement or determine the vertical displacement of joint C. So at this point, due to the applied force, which is 8 kilonewtons load laterally. Okay, so and they have 2 cases. First is you need to find out the vertical displacement at joint C due to the applied load. Another case is we need to calculate the displacements of joint C due to the fabrication error. So given that the member AB is shortened to 5 mm. So in this case, there is no effect of applied load. Okay, so they have two cases here. First, the displacement due to the applied load. Another one is the displacement due to the fabrication effect. Okay, let's discuss in detail on this problem. Okay, first let's look on the first part of this equations, which is on the effect of a displacement due to the applied load. Okay, so basically for this particular virtual method, so actually there is nothing much different with the beam with a virtual method. So you need to provide two set of diagram, which is a virtual, which is a real diagram, and another one is a virtual diagram. What you can see in this slide, this is the real diagram. Okay, so where with the applied load 8 kilonewton load. Okay, so and as usual, you need to find out all the reaction forces at the support. So I don't want to discuss in detail. You can see here the value of reaction at support, and you can proceed to calculate all the internal forces. So in the member by using the method of joint. So for instance, here you can see that by considering the joint A. So you're gonna solve for the member FAC and the member of FAB. So, and you can see that the value of FAC is equal to 5 kilonewtons and FAB equal to 4 kilonewtons. So I don't want to discuss in detail how to get this. Basically, we have discussed in detail how the method of joint can be used to calculate the internal forces in the previous lecture. Okay, so proceed with a joint B to find out the internal forces in member BC. Okay, so and so once you have completed to determine all the internal forces based on the real diagram, you can proceed to find out the value of internal forces based on the virtual diagram, which is referred to the small end. So this is referred to the capital end. Okay, so the small end here, you need to apply the 1 unit load. Okay, since the problem is about vertical displacement of joint C, so you need to apply a 1 unit load at point C vertically. Okay, so what you can see here, so 1 unit load has been applied at joint C vertically downward. Okay, so and find out the reaction at support based on this free body diagram of virtual work, and then proceed with the internal forces and the member. Okay, so for instance, here you can see that this is the step to find out the internal forces in the member AC and AB by considering the joint A. Okay, so and proceed with the joint B to find out the internal forces in the joint in the member BC. Okay, so once you have obtained all the internal forces for the real diagram and the virtual diagram, you can tabulate all these values in the table. So what you can see here, this is values of axial force based on the virtual diagram. So this is the axial force based on the real diagram, and you can indicate the member number and the length of each member, and you can find out the value of nominator part, which is referred to in the equation, which is referred to N and L. So and you can sum up all the nominator part of the equation, where in this case it is equal to 21.344, and you can further calculate the value of vertical displacement by dividing this value of nominator part with the axial rigidity of a truss system. So where the area is a constant, which is equal to this value, and the E is equal to 200 GPa. So by simplifying this, you can see that the vertical displacement of truss structure at the point C is equal to 0.267 mm downwards. Okay, so that is the value of displacement due to the applied load. So let's move to the second equation, which is the displacement effect. Okay, due to displacement value due to the effect of fabrication error. So in this case, the fabrication error is due to the shortening of a member AB with amount of 5 mm. Okay. So in this case, you can see that the solution in this slide, where I have mentioned these equations for the fabrication error. So the displacements in the member due to these effects can be obtained by using this equation, which is equal to summation of N delta L. So the N is referred to NAB, so the member that has been affected, which is member AB. So by looking on the diagrams, member AB is the N is value is 0.667. So you can see that here this term has been substituted by the 0.667. So and the delta LAB is referred to the value of shortening in a member, which is equal to 5 mm. So convert it into a meter, so you'll get 0.005 meter. And here I want to highlight that you can see that here there is a negative signs indicate the shortening. If the member is stretching along, you need to put a positive sign. So the negative for the shortening in member, so the stretching in member, you need to put a positive sign. So I hope that you can notice these things when you use this particular equation. Okay, so simplify this, you can see that the displacements at the joint C is equal to negative 3.335 times 10 to the power of negative 3 meter. So convert it into millimeter, you can see that the displacement is 3.335 mm, which is, you can see the arrow is upwards. Okay, so meaning that this effect of fabrication error has been caused the joint C move upwards. Okay, so if you look on the effect due to the applied load, so the displacement is downward. Okay, so the last part, which is not asking in the question but presented in this slide, where the displacement due to the combination of both effect, which is what you can see is effect due to the applied load and effect due to the fabrication error. Okay, so we have calculated the value of each cases, where this is equal to the value of a displacement due to the load is equal to 0.267 mm the downward. Meanwhile, for the fabrication error effect is equal to 3.335 mm the upwards. Okay, so by total up both of these effects, you can see that the value of displacement, the net displacement of this joint C for the truss system is equal to 3.06 mm, which is upwards. So in this case, you can see that the fabrication error has governed the displacement in the structure system. Okay, so we have done for the example 4, and let's proceed with another example, which is example 5. So in this example, we have a bit complicated truss structure system as compared with example 4. Okay, so basically these examples, you can see that we have a truss structure system with different cross-sectional area that indicate in each member in the diagram. Okay, so this truss structure system is loaded by the joint load or the nodal load, where it is 10 kN at the joint B and 15 kN at the joint C. Both of them is downwards. Okay, so you can see that they have three equations that we need to discuss here. Okay, basically it's all these three equations differ in the case. Okay, for the first case, you can see that we need to calculate the vertical displacement at the joint C due to the fabrication error, where the member is 5 mm too short. Okay, so the first case, you need to take into account of the load effect, including the fabrication effect. So the second case, you can see that obviously indicate that you need to remove the loads. Okay. So, and you need to calculate the vertical displacement of a joint B. Okay, for the joint B, where the member AB and BC experience a temperature increase of 110 degrees Celsius. So, given that the coefficient of temperature change is equal to 1.8 times 10 to the power of negative 6. Okay, so in brief, so the second equation is about the displacement due to the temperature change. Okay, so no load effect will be considered in this second equation. Okay, meanwhile for the last equations, remove the loads. Okay, so meaning that no load effect due to the 10 kilonewton and 15 kilonewtons at joint B and C respectively. So the vertical displacement at the joint B must be calculated based on the effect of a fabrication error. But here, the effect is 19 mm too long at this particular member EB. So in the first part, but the first equation is shortening of the member EB. So the third equation is about the stretching of the member EB with a 19 mm amount. Okay, let's go one by one. Let me discuss one by one all of this question. Okay, so let's start with our first question. Okay, the first question is about we need to find out determine the vertical displacement at a joint C. Okay, so given that the information here is the member EB is 5 mm too short. Okay, so in this case you need to okay, since we use the virtual method, so you need to provide two diagrams, the real load free body diagram and the virtual load free body diagram. Okay, so for the real load, you just copy down the actual diagram in the equations and find out all the internal forces in each member. And for the virtual load diagram, so you need to apply 1 unit load, okay, at the joint C downward, since we need to find out the vertical displacement at the joint C. So you need to apply 1 unit load at the joint C. Okay, so then you can calculate all the internal forces based on the virtual load diagram. Okay, as what you have done for the real load diagram. And so once we have determined all the internal forces for both of this diagram, you can tabulate all the values of internal forces in a member as what you can see in this table. Okay, so the lengths you can see the member in this truss have different lengths, so we can tabulate in this column. And this is a value of internal forces based on the real diagram. So this is internal forces in a member based on the real diagram and based on the virtual diagram. Okay, so as usual, find out the nominator part of the equations. Okay, so and given by this value 0.001007 and divide by the AE, which is the axial rigidity of the truss structure system. Okay, so this problem is about the vertical deflection at joint C. So the total displacement at joint C, okay, for this equation you need to take into account of the load effect and the fabrication error. Okay, so the load effect is given by this value. Okay, so meanwhile for the fabrication error is given by this value, which is the N is referred to the N for the member AB. So you can see that this is a member EBE or EB, so which is equal to 1.414. Okay, so multiply with the shortening value, which is 5 mm. So since it is too short, so you need to indicate the negative sign in the equation. So and simplify this, you can see that the vertical displacement at the joint C is equal to 6.063 mm upwards. So you can see that the value is negative. Okay, so and then here you can see that the arrow is upwards. So and again, this truss structures is governed by the shortening effect instead of the load effect. Okay. What you can see here is this is the load effect give positive value. So the shortening effect, the fabrication effect is give a negative value. So obviously the shortening value is larger than the load effect value. So that's why the net value, the total value of displacement at joint C is upward, meaning that this structure system, the displacement for the joint C is governed by the fabrication error. Okay, so let's move to the second questions, which is on the vertical displacement of a joint B, of a point B, where member AB and BC experience a temperature increase of 110 degrees Celsius. Okay, so in this case, we still at a joint B as what we have done in the first part. Okay, So meaning that you can recycle the value of internal process for the real keys and in the virtual keys. Okay, so you are not required to recalculate the value of internal process in the Truss structure for the virtual keys. Okay, because the same point has been considered, unless different points considered. For instance, let's say at the second questions, the joint the joint C. Okay, so find out the vertical displacement at the joint C. For this particular problem, you need to recalculate the value of internal forces for the virtual diagram. Okay, for the real diagram, remain the same. You can recycle to use that value. But if the question asking different joints, you need to recalculate the value of internal forces for the virtual diagram. But in this case, the point remain the same, so you are not required to recalculate the value of internal forces based on the virtual diagram. Okay, so you just recycle the value in this table. Okay, so we need to in this second part, the question indicated that you need to remove the loads, meaning that the load of 10 and 15 kilonewtons not being considered in the analysis. So no effect of displacement due to the applied load. Okay, so this is equations that you have seen in the early part of this lecture, where the equation due to the temperature effect is given by the summation of n alpha delta TL. Okay, so the member that has been affected is a member A, B, and B, C. So you can see that since they have a two member affected, so you need to have a two term. So the first term for the AB, the second term for the member BC. So if you have if there is three members or four members affected, so you need to have three term or four term based on the numbers of a member that has been effects in the system due to the temperature causes. Okay, so since member AB and member BC is the only members that affected due to temperature increase, so in the solution you can see that they have a two term. Okay, so and then at this stage we just simply substitute the value of n alpha delta T and L. So NAB and NBC can be obtained from this table, where NAB is equal to -2. NBC is equal to -1. So you can see that here, -1 for NAB. Okay, NAB. And NBC is equal to NBC equal, okay, NBC is a 0. Okay, NBC is 0. Oh, sorry, I have made a mistake here. Basically, the first part asking about the vertical displacement at the joint C, the second part asking the vertical displacement at the joint B. So in this problem, you need to recalculate the value of this internal forces for the virtual work diagram. Sorry for that. So I have make a mistake on this. Okay, so for this second question, you need to recalculate the value of internal forces in the member based on the virtual load diagram. So you can't use this tables for the n value, the small n value. So you need to recalculate. Okay, so you need to carry out the joints method of joints, or basically you have another method that you can use. We call it as an easy method. So I'm not going to discuss how to use that easy method. I'm going to discuss that method in different sections. Okay, so to accelerate the process of calculations for the internal process in the truss structure. So okay, so in short, you can see that the internal process for member AB is equal to -1. So the internal process for the member NBC is equal to 0. So that's why you can see that the term for the second term for member BC is a 0, because NBC result the 0 value internal process based on the method of joint, which is not shown in this slide. Okay, so given that the alpha is equal to this value and the increase in temperature is a 100 ton, if the decrease in temperature, you need to put a negative value. Since this increase, you just put a positive value. So simplify this, you can see that the displacement at the joint B is equal to negative 2.376 times 10 power of negative 4, or equal to 0.2376 mm. So which is the displacement is upwards. Okay, so which opposite from the from the displacements of truss structure system applied. Okay, so in this case, you need to apply. I forgot to explain that you need to apply one unit at the joint B. Since our interest is to determine the vertical displacement at the joint B. Okay, so and part 3 of these questions, we need to find out the displacements at the joint B. Where the member EB is fabricated 19 mm too long. Okay, so and in this part, you need to remove the loads, meaning that no effect from the applied load of 15 and 10 kilonewton load. Okay, so no effect from this both of this load. Okay, so the equation that you need to use is fabrication's equation, which is equal to summation of n delta L. So since only one member affected, so you have one term in the equation. If more than one, if you have a two member or three member affected, you need to have two or three terms in the equation. Okay, so based on this problem, the member EB is affected, that we want to calculate the displacements of a joint B. So apply one unit load, meaning that you can recycle to use the internal forces based on the visual diagram in the previous part, which is a part 2. Okay, so the value of NEB is equal to 1.414 kilonewtons and the LEB is equal to 19 mm. So the value of vertical displacement at joint B is equal to 26.87 mm, which is downward. Okay, so we got positive value, meaning that the displacement of the structure system due to the fabrication's error is parallel to our assumption of one unit load downwards. So if you look on this case, on the temperature effects, so we assume that one unit apply downwards, but in a final answer we got negative, so meaning that it's opposite from our assumptions. Okay, so that's it for this session. So we have discussed all the example and solutions with the solutions for the visual work method. So in the next session, I'm going to focus on how we can use the easy method to accelerate the calculations of internal forces in the truss structure system. Okay, so thank you for listening. So see you again.